Welcome to The Explainer. We're often told the universe has a hidden language. Well, today we're going to look at a secret code that isn't written in letters or symbols, but in something we use every single day: simple whole numbers.
I mean, it sounds like a riddle, doesn't it? What could ancient math possibly have to do with you checking your bank balance? But the answer? It's literally the invisible engine that powers our entire digital world. It's the silent guardian protecting your most sensitive information.
And that engine, that guardian, is a field of math called number theory. All it is, really, is the study of whole numbers, integers, and all their hidden properties. And trust me, it is way, way more important to your daily life than you probably think.
All right, so where do we even begin with this stuff? Well, believe it or not, we're going to start by going all the way back to something you probably learned in grade school, but we're going to look at it in a completely new light.
So, divisibility. I mean, it's a concept we all kind of get, right? You know that 3 fits into 9 perfectly, but it doesn't fit into 17. It's that simple idea, one number fitting neatly inside another, that's actually the very first key to unlocking the hidden structure of all numbers.
Okay, so if dividing is the action, who are the main characters in this story? What are the key players in this whole numerical world? Well, it turns out there's a very, very special class of numbers we need to talk about.
And those key players are the prime numbers. The best way to think about them is like the atoms of the number world. They are the fundamental building blocks, the particles that just can't be broken down any further by division. They're it.
Yeah, and it's just as important to understand what isn't a prime. Take the number 1. You might think it is, but nope, it's not prime because it only has one factor, itself. The rule says you need exactly 2. And a number like 9? That's out too, because you can break it down into 3 times 3. Getting this distinction right is absolutely crucial for everything that comes next.
So you take these prime atoms, right? And you can use them to build basically any other whole number you can think of. But here's the really amazing part. They do it in a super specific and predictable way.
This idea has a big, fancy name, the Fundamental Theorem of Arithmetic. But what it means is actually pretty profound. It means that every single number has its own unique prime fingerprint. It's like a special ID tag made of prime numbers that belongs to that number and only that number.
So, let's actually see how this works in practice. We take a number, say 1820, and we just start breaking it down. We divide by the smallest prime that fits, which is 2. Then we do it again. Then we move on to 5, then 7, and we just keep going over and over until we can't go any further. And what are we left with? 2 2s, a 5, a 7, and a 13. That is its unique prime fingerprint. I mean, think about it. No other number in the entire universe is built from that exact same set of primes. How cool is that?
Okay, so pretty cool, right? Every number has a unique prime fingerprint. Now I want you to completely shift how you're thinking. Let's look at numbers from a totally different angle. From now on, we're not going to care about how many times a number divides another one. Instead, we're going to focus only on what's left over, the remainder.
This whole new way of thinking is called modular arithmetic. You could just think of it as the math of remainders. And it might just look like we're changing the notation a bit, but believe me, this focus on what's left over is the secret key that unlocks pretty much all of modern cryptography and computer science.
And here is its superpower. With modular arithmetic, you get a choice. You can do some gigantic, messy calculation first and then find the remainder at the very end. Or you can shrink all the numbers down right from the start by finding their remainders first and then do the super easy calculation with those tiny numbers. Either way, you get the exact same answer. It's like the ultimate mathematical shortcut.
So that's the crucial point here. These properties, they give us this incredible shortcut. They let us take on problems that seem just impossibly huge and shrink them down to something we can actually manage.
All right, let's put this shortcut to the test. How would you even begin to calculate 9 to the power of 10 mod 5? I mean, 9 to the 10th power is almost 3.5 billion. Trying to figure that out and then divide by 5 to find what's left over? That sounds totally impossible without a supercomputer. But with our new friend modular arithmetic, it's shockingly simple.
Okay, you ready? Let's walk through this little magic trick. First step, instead of dealing with a big old 9, let's just shrink it down right away. What's 9 mod 5? Well, the remainder is 4. So our huge problem just became 4 to the power of 10. Okay, it's better, but it's still pretty big. Now for the clever part. We can rewrite 4 to the 10th power as 4 squared to the 5th power. Now why on earth would we do that? because now we can simplify what's inside those parentheses. 4 squared is 16, and what's 16 mod 5? It's just 1. Suddenly, our impossibly massive problem has completely collapsed into just 1 to the power of 5. And we all know what that is. The answer is 1. We just solved a problem involving billions in our heads.
And that exact trick, that amazing ability to work with these enormous, crazy numbers by simplifying them down into small, predictable remainders, that is the very foundation of modern cryptography. It's the reason it's so easy for your phone to encrypt a message, but nearly impossible for some hacker's massive supercomputer to crack it.
So you see, number theory shows us that behind all this immense, mind-boggling complexity in the world, there are often these elegant and surprisingly simple rules at play. It really makes you wonder, doesn't it? What other secret codes are just out there, waiting for